hell yeah. So we have dynamics, and we got a starred problem. We're doing differentiation, and for sure. So we're going to try to do this just kind of all in one go. I have not seen this problem. It doesn't have an answer in the back of the book. But we're going to try to figure out if we can do this. So one thing that I like to do is just kind of use the picture that they have. So I'm actually just going to kind of slide this out because we are going to use our ruler. Now we've done similar problems like this. We've done a similar problem like this before, so we need geometry. It says that we want to, as this thing is wonky and spinning around, this thing is going to go up and down. And so let's at least do that. So this disc is pivoting from like a off center, and so when it's hanging down here, the disc is going to be about like right there. So if the disc is right there, this thing is going to be right there. Okay, hell yeah. And then let's figure out what the highest location of this thing. When this disc is like has the highest point up there, kind of at a perpendicular angle, hell yeah. So maybe this thing can get up to a pretty high angle, maybe greater than 60 degrees. Okay, and then the problem statement says when theta is 30 degrees, holy Toledo. Oh, this is fascinating. So it says when theta, this angle, is 30, which is pretty close. It says calculate the angular speed of the follower. Oh, yeah. So we want to just, at this angle, we want to know how much this is changing. Okay. Yeah, that's fascinating. Okay, so yeah, so and this angle B already is established. So at about 30 degrees, this angle is going to be, I would say, maybe even 45. I would say this angle is going to be a little bit less. And so let's take a look at this disk again. If this angle comes flat, if beta comes to 0, then the disk is just all this way. Cool. And then so when we increase that angle to about 45 maybe, this rod is going to be at a 30-degree angle. Now the angular speed of this disc is usually measured from its initial angle. So we're going to say its initial angle was horizontal right here. And then the angle gets played out in this direction. So unless it says otherwise, this circular cam has a constant angular speed of 8 radians per second. Here's the arrow, so we're going to assume that that speed is this direction. Okay, booyah. So what we're going to try to do is just try to get at least somewhat of an answer. So we're going to go back to that location that this thing would be at a 30-degree angle, and now we're going to rotate the slider. I don't know. So this distance is 5 inches. So when this angle is 90, I'm just going to say when this angle is 90 and then over here. So like 90 plus 45. Let's break out the calculator. 90 plus 45. When this angle is 135 degrees, I think this thing is going to be up at an angle about like that. Maybe just say 70 degrees. Okay, cool. And then, that's going to be at 90 plus 45. And now I'm going to say at 45. I'm just going to, what I'm trying to do is just get an overall general gist of what's happening with this problem. And hell yeah, sometimes that's hard, you know what I mean? Because you want to maybe do more analytical steps. One thing that is really helpful is just cut it out with, like blow it up and then cut it out and then pin it to your paper and then actually spin this disc. And but for this video, I don't want to do that. I just want to use kind of my, put on my thinking cap. So I'm going to say at a 45-degree angle, this is going to be about 30. So there you go. Those two statements that I have. So when this angle is 45, it's going to be at 30. And then if I increase this angle to 135, it's going to go up to 70. So I'm going to say the angle, this theta is going to change from from 30 to 70, so 30 degrees to 70 degrees, that's a change of 40 degrees. And when beta changes by, beta is going to go from 45 to 135. So this beta is going to change from 45 degrees to 135 degrees. That's a change of 90 degrees. Okay, hell yeah. And we're going to, this thing has a constant angular speed. So this angle beta is it's a constant speed. And we know that's going to be 8 radians per second. So we need to draw a circle. And this is our radius. You know what I mean? Always pretend like you're like measuring a string of the radius, draping around the circle. Hell yeah. That distance is going to be 1 radian. And there's 6 of those. You could drape this string about 6 times around this circle, and it's 6.28. But 6 is a good reference point. Sweet. So every 60 degrees is 1 radian. And so we swept out an angle of 90 degrees. So that's going to be 1.5 radians. So 1.5 radians. This thing is spinning at 8 radians per second. So every second, this circle is going to spin once plus, just past 90. So it's, hell yeah, it's gonna spin 120. So 360 plus another 120. So every second, almost a revolution and a half every second. Cool. But because we know, so what do we do with 8 radians per second, and we know it's going to rotate 1.5 radians? How do we get seconds? We divide this number with this number. Seconds pops upstairs, and we're going to have 1.5 divided by 8. Do I know that? Nah, but I do know that 1 divided by 10 is a tenth of a second. Cool. So is that fairly close? 1.5 divided by 8. Well, that's more like 1.5 divided by 10. That's going to be 0.15 seconds. But this is a bigger number. So hell yeah. Maybe it's like 0.185 seconds. Okay, hell yeah. And then let's throw it into our calculator. So that's kind of the skills that I use to beef up my mental math. And booyah, we were pretty much right on. 0.1875. So I guessed 1.85. That was a pretty good guess. All right, hell yeah. So now we actually have, even though the distance from 30 degrees to 135 is a huge change in angle. You know what I mean? But it gives us a start. It says that the angular speed of this in radians is going to be radians per second. It's going to be angular speed is change in angle, change in time. And we have a change in angle of 40 degrees. Okay, hell yeah. That's going to be about 0.6 radians. Because 30 degrees is 0.5 radians. 60 degrees is 1 radian, we said. So you could do 1 radian is 60 degrees, so 1 times 40 divided by 60. So yeah, it's 0.66. So we have 0.66 radians. I'm just going to store that as x. In how many seconds? 0.1875. So divided by 0.1875. So this is our angular speed. Angular speed of this thing, we're going to say of AB, is 3.5 radians per second. Now, that is totally a guess, and it's not representative of exactly at 30 degrees, because we went from 30 to, we went from 30 to 70, you know what I mean? So we went too far. We need to do a less representative change in angle, be more precise with our calculations, and then be more precise with our change in time. But hell yeah, this gives us a start. And so one thing we do know is that the angular acceleration at 30 degrees is going to be in the positive direction, and we know kind of its magnitude. So right there it's a pretty decent start without cutting this out and making it into a project. All right, booyah. So now, kind of for step 2, is to do some geometry. So on this, I do know that we're going to have a tangent from the center right to wherever this follower is. So that's going to be a 90-degree angle. And this is going to be the radius. Okay, sweet. Let's see what else we know. Yeah, this might be a brutal one. But from... Yeah, and then we have to incorporate this angle beta, maybe, at some point. Oh, okay. Well, no, I mean, this is the hard part about these problems. You're just like, damn, like, what do I do? Yeah, so, yeah, the geometry is everything. We need to relate these two angles. And yeah, it's not an easy task. We do know that this distance right here, which should be a hypotenuse of, at some point, we can, yeah, so we can easily do this. From the other problem, we learned that we can connect those lines right there. And in the other video, I called that distance y. What we did is we came in here and made a 90-degree angle there and there. That doesn't help us, though, because, like, right now I still don't know... Oh, no, I do know. Like, I can say that this intermediate angle, I'm just going to call it phi, is... So, I don't know if that's going to be helpful, but because we have a straight line here, like 180 degrees is going to be theta plus phi plus beta. But yeah, I don't know if that's going to be super useful. All right, hell yeah. So let's keep crushing. Yeah, where else can I get... I'm just looking for kind of right triangles. Like, where can I get right triangles? All right, so, I mean, this was the first one. So if that's a right triangle... That was the one thing I was just like, well... Now, the perpendicular distance between these probably doesn't always go through that point. That's also the harder thing to look at, too. Because I'm going to look at this line. If this rotates... Oh, this is interesting. Alright, hell yeah. I don't want to do a lot of thinking off camera, but I do know one other thing, is that if we do know this angle, I can come up here and draw a perpendicular line. This probably isn't going to help at all. But if this is the angle beta, I know that this is also beta. But again, I don't think that's really going to be useful. Alright, hell yeah. So I think I came across something. It was just like, holy Toledo. Because some of the principles of these problems are like, hey, we know this eccentricity, and then we know this radius. So these are the two things that are constant. They're also the things in these problems that are... well, sometimes in one problem they were the hypotenuse, but I guess that doesn't... matter. Like, at the end of the day, what you're trying to find is right triangles, and if they involve this eccentricity, or if they involve this radius, I mean, you at least know one thing about the triangle. And so what we're hoping is to know we need to know two things about the triangle. If we know two things about a triangle, we know everything about it. So, and then I was just like, okay, so if I have, this is my eccentricity, you know, just start making a right triangle to things. And so I did that, and then I came in here and did that. And then I was just like, well, this one didn't really help. But then I went to this radius, and I was just like, oh, okay. This for sure makes a right triangle. And then draw it out. Okay, it makes a right triangle with this and this. And then I was like, well, that's not theta, but guess what? This is the eccentricity, and this makes a right triangle. So it took me that long. I thought about it for 5 minutes off camera, but you're seeing this real time. So I don't know, you know, how you're going to like get better at that, you know, because I don't even know if I'm on the right track, but no, I think I'm totally on the right track now, because and that was cool, because that oh man, yeah, no, that involved this eccentricity. This is beta right here, and if I know beta and this eccentricity, this hypotenuse, I can know all the. I can know this side, and if I know this side, then hell yeah, then I at least know one thing about this triangle right here, and this triangle, you know, has a common side right here with this triangle. This triangle, I know this radius, and booyah. So still, I still might be stuck. So let's grab a fresh sheet of paper. And one thing that I will do is I'll probably blow this up, just so we can get a better look at it. But for the time being, I'm okay with it where it is. Alright, so yeah, from this point, there we go. Here's our 90-degree angle. Cool, so we have a radius there, right triangle. And so I'm going to call this theta 1 and then this theta 2. And then we're going to say theta is equal to theta 1 plus theta 2. Hell yeah. This is my eccentricity here. And so this is beta. So, I mean, I do know that this distance is beta, E cosine beta. But more importantly, this distance right here of that triangle will be E sine beta. Okay, sweet. And I for sure know this. Oh, and it gives me this distance. I totally spaced that it gave me that distance. For whatever reason, I thought I didn't know anything about this. But hell yeah, now we're on a roll. Because I was just like, it would be sweet if I knew this part of this triangle. And I do. This part of the triangle is going to be 6 inches plus E cosine beta. We just spelled it out right there. I totally just didn't even look at that. Okay, and so, hell yeah. So we know what this triangle is. We know everything about this because we know this distance E. We know this distance, this angle beta, this distance E. We already got it. Let's do it again. Sun is shining on the sinus, so this is E sine beta. And then this distance is E cosine beta. Hell yeah, and this distance is 6 inches. So now we know this full distance in terms of beta. And what we're trying to do is link beta with theta. Like, we're going to know beta because it's spinning at a constant angular speed. And so, but when we need... what do we actually need? Yeah, we need an equation for theta as a function of beta. Once we get that, then we can take the derivative. We can take the derivative of this with respect to time. But the only thing is like we're gonna have like whatever beta plus whatever beta. If we take this respect to time, I don't have time right here. So what I'll do is I'll take this respect to beta and then use chain rule, and then we'll go d beta dt. and this is beta dot. Beta dot, which is omega of omega of beta or whatever. And so angular speed, and we already know that it's 8 radians per second. So but if we already know that it's constant angular speed, we know that beta is equal to beta is equal to beta dot, that's the angular speed, times time, which typically you would write it as just omega t. We see this a lot, but in this problem it's going to be beta dot t. So anywhere where we see the angle beta, we can just replace that with beta dot t. We'll do that at the end, and then we'll put this into derivative calculator and solve for angular speed and angular acceleration. We'll find the angular acceleration at that 30 degrees. All right, booyah. So now I definitely feel like I'm on a roll. So we know everything about this triangle. And since, and that's the other thing. So we have a side and a side. This is where you for sure want to bust out Pythagorean's theorem. You know, always, anytime you're doing trigonometry, write Pythagoreans. And if you're not well versed with Pythagoreans, you know what I mean, write it in a bunch of different ways. We're going to say this hypotenuse is a squared plus b squared square rooted. Hey, let's say I want to just find a. That's going to be c squared minus b squared square rooted. If I want to find b, that's going to be c squared minus a squared square rooted. So you see, or maybe you don't see, but like this one, hypotenuse, yeah, that's classic. But if you wanted to find a side, you have to take the hypotenuse squared minus the side squared. So that's the only thing, and that should make intuitive sense. You're taking the hypotenuse is the larger number. That's why sine or cosine is a percentage. Sines and cosines are percentages of that larger number. You know, so anytime you see sine theta or cosine theta, just think percentage of the hypotenuse. Hell yeah. And so to get the side, hell yeah, you're going to take the hypotenuse squared minus one of the sides squared to get the other side. In this case, we just need the hypotenuse. So we're going to say this distance right here, and I guess, yeah, let's classically call it c. So we're going to say c is equal to the square root. We'll do this one first. E squared sine beta squared. Okay, so that's taking this squared. You know, I just kind of squaring something that has a product. You know what I mean? You can just square each term. So that's what we do there. And then we're going to plus this one. We have to do parentheses. We have to say 6, and this whole thing's in inches. Cool. 6 plus e cosine beta squared. All right, but my hunch is let's do that because maybe we can kind of simplify. Like, I don't care. I'm going to throw it in the derivative calculator. But let's do this. So if we have, anytime that I have 6, so we're going to have 6e cosine beta. Anytime I have something squared, I'm just going to square the first term. So that's going to be 36. Then I'm going to square this term. That's going to be e squared cosine squared beta, or cosine beta squared. And then I'm going to multiply the two terms together. And that's going to be 6e cosine beta, and then double it. So I'm going to go plus 12e cosine beta. And so when we do that, we're going to add it to e squared sine beta squared. And what I'll notice is that we have e squared sine squared beta plus e squared cosine beta squared. You know, so sine squared plus cosine squared is 1. So these two terms right here will just be e squared to the 1. Cool. And so, hell yeah, we can kind of simplify this. So that distance c is going to be, I'll just do it first. We're just going to have e squared. So we have e squared, perfect, that's that thing. And, yeah, these are just kind of, yeah, so a portion of this is going to add to this to get e squared times 1. Cool. And then we just have these two remaining terms. So we have plus 12e cosine beta plus 36. Okay, hell yeah. So that's going to be the hypotenuse. And the cool thing about this is, well, I don't know what the cool thing is, but, oh, because I was, like, I don't even know if we needed to do that, but yes, we did. We needed to do that because this triangle, I need to know two things about it. I only know it has a radius, and that's going to be a constant, and that radius is 3 inches. But I need to know something else about this triangle, and hopefully it's related to beta, which I will know. Alright, sweet. And so so that thing that I now know, I have a right triangle, I know two things. So that's going to be one of the fundamental, I don't think anyone ever taught me that. You know, just keep repeating it. If you have a right triangle, all you need to know is two things. Once you know two things, you know everything about that triangle. So we know this radius, and we know this side as a function of beta. Sweet. And so that is going to get us this theta 2. So we can say theta 2, we're going to relate the hypotenuse and the opposite for theta 2. So that screams opposite over hypotenuse is sine. So you can just write it out. If you're new to this, you would say sine theta 2 is opposite over hypotenuse. But I just want to know the angle. So I'm going to say this angle is the inverse sine. So see, I take this inverse sine, take inverse sine of both sides if you want to, or I just like to think of it just moving the inverse sine over there. Hell yeah. So we're going to have inverse sine of the opposite, which is r, divided by this. So hell yeah, we're going to have inverse sine of r divided by e squared plus 12e cosine beta plus 36. Alright, just kind of double checking, making sure we did good. Okay, booyah. So that's theta 2, and we could have gotten theta 1 a long time ago. You know what I mean? We already knew that it was, and, you know, there's many ways we could get it. We could still use this hypotenuse, and, you know, or we could just say the tangent. You know, those are the two first things we found out about that triangle was e sine beta squared. I mean, just e sine beta, like this side, and then this. So we can say that theta 1, we'll say inverse tangent. And it's good to work on your skills of just going to the inverse tangent, knowing that the inverse tangent still will be the opposite. So we're going to say theta 1's here. Sun is shining on the sinin. Know that tangent of an angle is the sine component divided by the cosine component. So if you're trying to find the angle, that's going to be the inverse tangent still of the sine component divided by the cosine component. So that's where, even though we're doing the inverse tangent right away, you can still say tangent of theta 1 is this opposite over adjacent. And so even though we're just taking the inverse tangent, just trying to go for it, that's going to be a skill that will really help your engineering of just being like, hell yeah, I want to know the angle. What do I know about this? I know this side and this side. Neither one of them are hypotenuse. And so tangent. You could use cotangent if, you know, sometimes you want like the nicer, yeah, this is a good teachable moment. So why would you use tangent or cotangent? Well, if you want to look ahead, if I do tangent, I'm going to take this, e sine beta, divided by 6 plus e cosine beta. You know how you divide something like 1 divided by 1 plus x? You really can't do anything about it. But if you had 1 plus x divided by 1, oh hell yeah, that's just 1 plus x. You know, way simpler. So that potentially is why you'd want to do cotangent. Inverse cotangent right here, because then you'd have this 6 plus e cosine beta. A cotangent's adjacent divided by that. But that aside, who cares? And we're going to do e sine beta divided by 6 plus e cosine beta. But no, if I was doing this by hand, like right now I know to do that. I've done enough of these problems where it's just like, I'm going to have to take the derivative of this at some point, and y, you know what I mean, like make it simpler. Like flip it upside down, do the cotangent. Okay, hell yeah, so we did it. Now we have theta is just the additive things of both of these, and they're in terms of beta. And we know that beta is going to be beta naught t. So literally we have it on one sheet of paper, and now I'm going to throw this into the derivative calculator, and this is blowing my mind. All right, booyah. And do I even need to rewrite them again? All I'm going to do, sure, I'm going to add this to this while putting in b dot t. I really don't want to put in b dot t. I really want to put in omega t, just because omega is just such a good symbol for angular speed. And I think I will. I'm going to say b dot is omega. Because then in the derivative calculator, I want to see this omega. It's just, the symbol is just really easy to see, and I don't want to confuse it with b as just an angle. Cool. So that's my plan, and so we're going to take inverse tangent of e sine omega t, hell yeah, divided by 6 plus e cosine omega t. Hell yeah. Alright, that's simple as. And then plus, and see how it's a function of time? And then see how, like, hey, foreshadow, we're going to differentiate this as a function of time, and differentiate all this jazz, as a function of time. Hell yeah. So but anyway, we need to figure out what this angle is given any beta, or this angle given any time. That's basically what we're doing. Theta 1 plus theta 2, and then we're square. Alright, so we have r divided by square root e squared plus 12e cosine of omega t plus 36. Man, this is one of the, like, for a starred problem, this one's turning out really well. But see, like, I'm so glad I did it this way, because the thought experiment is like, how do you see this geometry? One, you have to know like what you're actually trying to do. You're trying to find this angle in terms of beta, but you have to do it using geometry, usually right triangles, you know, because that's if you have a right triangle, hey, we have these things called sines, cosines, and tangents, and they're programmed into our calculator. They're literally Taylor series, you know what I mean? It's literally like going onto a chart on the wall and being like, hey, if you have this ratio, you're going to have that angle of, you know, it's all nonsense anyway, but it's calculated nonsense where our world runs on sine, cosine, and tangent. So we just go with it, and but hell yeah. So yeah, right triangles are king. And that's society. All right, so hell yeah. So we do have this, and we're going to take the derivative with respect to time. So let me throw it into the derivative calculator, and we're going to pop out at least angular speed, probably angular acceleration too, because I'm curious about both. And then we're going to compare it to our our first answer. We thought it was 3.5 radians per second. You know, do I think it's going to be faster? I think before we do this, it's also really good to get a feel of like, hey, when is the angular acceleration going to be the greatest, and when is the speed going to be the greatest? So when this is at its lowest point, like it basically comes down and this stops, or it changes direction. So everywhere it changes direction, I know that's going to be a point of highest acceleration. We have a velocity coming in, we have a velocity going out. Even though it comes to a stop, the change in velocity is going to be the greatest right there, change in acceleration, especially since you're going a velocity one way and then going a velocity the other way. And then also when it hits 70 degrees, same thing. Now one of those might be a greater change in, I think like when it's up here, I think that's going to be the greatest change in acceleration, and when it comes down here, it's so low for so long. like I did this problem, you know, with the pin connection right here, and at the lowest point, see, it stays so low for so long. So yes, you do have a spike in acceleration, but it's not as big as the acceleration at the top. You know, you're coming in hot and then you're leaving hot. Where here you're at the bottom, you're just going so slow for so long. You know what I mean? And then kind of at the halfway point is going to be your highest acceleration. You know, this thing's going to change with the highest amount of velocity. You know, the angular speed will be the greatest kind of at the 45-degree angles. Like from here, you know, dropping, I guess it's going the other way. So that's when it's going to have the highest angular speed. So yeah, even at 30, yeah, we're looking like, I think the angular speed is going to be increasing. I think the angular speed is going to be, you know, fairly decent compared, well, but I do think the angular speed is going to be increasing. I think we're also going to find that. All right, catch you on the flip side. Alright, hell yeah. So what we did is we put this in the derivative calculator. And so if you take the derivative of this with respect to time, okay, this is our input. This is the first derivative, and this is what you get. So anywhere where you see omega t, and then, you know, I had to kind of hold the phone because, you know, what is this omega t? We solved this in terms of beta. Let's see. Yeah, oh yeah, because I already plugged them in. So here was theta 1 and here was theta 2. So theta is going to be the addition of both of these. And it's in terms of beta, you know what I mean? So they want to know what the speed is. I mean, but we now have it in terms of just time. You know, we have the angle at any given time, but the time is going to be in relation to the spinning disk. They want to know when theta is equal to 30. Well, we have an equation for theta. It's right here. We just haven't taken the derivative. So they want to know when theta is 30 degrees, which is like 0.5, what, 23 radians. They want to know, well, what we need to do is like, hey, put in theta as 0.523 and then find what beta is. You know what I mean? So all of these are beta, but they're in 3 different locations, and I just don't even think you could actually, well, maybe, but I'll have to look at that again to see if you can even get an equation for beta. So what I did is I just put it in my calculator, got this to this side of the equation. I mean, or you don't have to do that. So what I did is I, you know, set this side equal to 0 or this side equal to 0.523 radians, and then moved it over to the other side. So we have negative pi times 30 divided by 180. That's 0.5 radians. And then add this and this. And then we graph it, and then we can solve for the 0 value. And what we're going to get is booyah. So that's going to give us beta when theta is 30 degrees, or 0.5 radians. And we find that beta is also 30 degrees when theta is 30 degrees. Cool. Another way to do that is, you know, if this is the equation, for theta, I'm just going to graph it. Cool. So how would we find where this equation is equal to 0.523 radians? Well, we would just come over here and then just put that in. We would go 30 pi divided by 180, graph that line, and booyah, everywhere where this line crosses, that's going to be where the intersection is going to be where beta is, where whatever this value is, that's going to be where theta is equal to 30 degrees. Okay, sweet. So we did that. And when we type that in, so what we have found is that beta is 30 degrees. We have taken this derivative with respect to time. And so our inputs when we solve this, like you know what I mean, our inputs are going to be time and the angular acceleration of the disk, which is 8 radians. So that's going to be beta dot. So beta dot is omega in this. And then our time is going to be, well, it's going to be the time when beta is equal to 30. So, you know, the angle beta is equal to beta dot time, or omega t. And so time is just the angle beta divided by omega. So that would be like 0.523 radians divided by 8 radians per second. And booyah. So that's what we type in right here. We basically take the pi 30 divided by 180. That's 0.523 radians. And then divided by that 8. So those are our inputs. So in the derivative calculator, you can put as many variables as you want. You're going to differentiate with respect. You got to choose one of these as the variable. So I differentiated with respect to time. And then since we have eccentricity, I'm going to call that C, because I can't input E. E is going to be a number in any math, with inputs. So, and then right here, here's our variables. We have the eccentricity. That's going to be 2 inches. So eccentricity is this distance from the center of the circle to the pivot point. That's 2 inches. Our radius is 3 inches. So 2, 3. Our angular speed is 8 radians per second. Here's the time when theta is 30. And hell yeah. So now this is going to give us theta. This is going to give us theta dot, and this is going to give us theta dot dot. So this is the angular speed is going to be 2.2 radians per second. Our initial guess, you know, from wherever, I don't even think I have that sheet of paper anymore, was 3.5 radians per second. I'm bummed that I think I left that paper upstairs. But anyway, so we're a little bit off from our initial guess, but we're close enough. And yeah, I'm gonna call this correct. You know, I think we did a pretty good job. If we wanted to hone in on the answer, maybe we could blow it up and actually do a diorama of it. I think I want to end this video. Man, I'm super tired. I want to go to bed, but we're gonna do this. So I'm gonna at least go through. I mean, see how even this first derivative is just hellacious. Like no one wants to do that. Like look how complicated that thing is. It's not necessarily complicated. It's just steps that, you know, get tedious, and you're just gonna make hella mistakes. So I'm gonna rewrite this equation for theta. So theta is inverse tangent. And I'm gonna save myself. I'm gonna say it's inverse cotangent, and then we're gonna put this on top: 6 plus e cosine omega t divided by e sine omega t. Hell yeah! And then we're gonna add it to inverse sine of. I mean, do we want to do that? I don't think so. I think we want to do inverse cosine. If we do inverse cosine, this just flips. And we'll have... And then I try to get everything stacked on the same level. So I'm just going to say this is r to the negative 1. And then even square roots. I get rid of the square root and just say this is bracket e squared plus 12e cosine omega t plus 36 to the 0.5 power. Okay, hell yeah. And let's see how we do there. And then even this can be rewritten as e to the negative 1 sine to the negative 1 omega t. Because then we won't even have to use the quotient rule. Now we will have to pull out, you know, if we're going to differentiate this with respect to time, hell yeah, we do have the time as a variable. But we have to pull out we have to figure out what the differential of cotangent is. I kind of know that one. It's -1 plus u squared du dx, or whatever, you know what I mean. But -1 divided by, so yeah, cotangent, -1 divided by 1 plus u squared. All right, cosine, derivative of that is going to be -1 divided by the square root of 1 minus u squared du dx. Okay, sweet. So let's try to do this as best we can. All right, hell yeah. So let's dive right in. We're going to have -1 divided by 1 plus this whole thing squared. So we're going to have 6 plus e cosine omega t. So this gets squared. Cool. And then we're going to have e to the -1 sine to the -1 omega t. That gets squared. All right, hell yeah. So basically just the inside gets squared. All right, we did it. And now we got to take the derivative of the inside. Okay, hell yeah. So we have a product of two things, like this is multiplied by that. So we have to take the first times the derivative of the second plus the second times the derivative of the first. Sometimes I just like to take the derivative of the first one just to get going. And all right, hell yeah. So we're going to do the derivative of this. 6 goes to 0. E is a constant, so we'll just say e -1, because cosine goes to sine. I guess I'm going to spell that out. So here's the graph of sine. Cool. Here's the graph of cosine. Sine, the tangent is 1 when it's 0, so that's going to be cosine 0 is 1. So sine goes to cosine. If this is the graph of cosine, the tangent at 0 is 0. So sine of 0 is 0. But this has a negative slope, so it's a negative sine. So derivative of cosine is negative sine. Hell yeah. So derivative of cosine is negative sine omega t. And then we got to take the derivative of the inside. That's going to be omega. Hell yeah. And now we're going to add, so that was the derivative of the first times the second. So now we're going to just go e to the -1 sine to the -1 omega t. All right, now we're going to take this first 6 plus e cosine omega t times the derivative of the second. So we're going to have e to the -1. This is to the -1, so we have to bring down the power. The power comes down. Oh, I shouldn't be doing this all crunched up. So the power comes down, and then we're going to take it sine to the -2 omega t. Hell yeah. And then we got to take the derivative of what's inside. That's going to be cosine omega t, and then omega. All right, whew, that was brutal. Okay, so that was that part. Derivative of this, and then we took the derivative of the inside. Okay, hell yeah, let's do this next one. So we're going to have minus 1 divided by the square root of 1 minus all this stuff on the inside squared. So we're going to have, if we have 1 divided by r and we square it, we're going to have 1 divided by r squared, so that's going to be r to the -2. So sweet. So we're going to have r to the -2, and then this squared just becomes what it is. So we're going to have e squared plus 12e cosine omega t plus 36 bracketed in. So we still got to bracket it in. Alright, so we got the square root of that. And now we're going to take the derivative of this, of everything that's on the inside of this. The radius is constant, so but we kind of have this the square root. So we're gonna take radius to the -1, bring down the power. That's going to be a half, and then we're going to have everything on the inside. 12e cosine omega t plus 36. We got to decrease the power by 1, so we're going to go -0.5. Okay, hell yeah. And then derivative of the inside. This is a constant. This is a constant. Cool. So we just have this. Fairly easy. So we're going to be 12e. Derivative of cosine is going to be -1 sine omega t. And then we'll have an omega. Whew, that was brutal. Okay, but we did it. Did the derivative of the inside. So there you go. So that's we did it. You know what I mean? This is this plus, you know, this, or this minus this. That is going to give us theta dot, or the omega of, do we have a picture of this? Hell yeah, of this AB. You know what I mean? This is going to go like this and this. And at 30, it's going to go in that direction. Positive. And we're even going to have positive acceleration. Look at this. So 2.2 radians per second. But it's also increasing in angular speed. Alright, booyah. And like what we could do is I could throw this into my calculator and see if I get the right answer. I just feel like I probably made a mistake, but there's no reason that I would make a mistake. So here we go. We're going to do pi 30 divided by 180. Okay, divided by 8. Whoa. That's going to be our time. So we're good on there. 8 is going to be stored as omega. You know, what other variables do we have? I just want to get that sheet. We have eccentricity is 2. Our radius is 3. I think that's it. E omega t. That's it. And just a lot of jazz. All right, so we're going to do -1 divided by 1 plus 6 plus alpha e cosine omega t. Cool. Another parentheses. Ooh. Yeah, that's good enough. Squared. Multiplied by alpha e to the -1 sine omega t to the -1. Okay. And then all squared. Holy hell. Okay. And then we got to multiply it by alpha e, alpha e to the -1 sine omega t, omega, alpha e to the -1 sine omega t to the -1 plus. Okay, so that was that, right? Or did we already mess up? No, we messed up. We should have a bracket here. You know what I mean? So I got to go back and then put that bracket in. Oof. All right, so we have e to the -1. So yeah, we're going to have another bracket there. Because this is the derivative of the inside. We got a couple components. So here's the next component. And we have 6 plus alpha e cosine omega t. I mean, just how ridiculous is this? It's way too big. Way too many places for errors. But if you can do this every once in a while and And you can find your errors too. Like you're setting yourself up to make errors to the negative 2. E to the negative 1, sine to the negative omega t to the negative 2. All right, cosine omega t, and then omega. All right, and then end bracket. Hell yeah. Now we're going to add it to a negative 1 right here, divided by the square root of 1 minus alpha r to the negative 2, alpha e squared plus 12 alpha e cosine omega t plus 36. Okay, hell yeah, that looks pretty good. Just kind of double check. Okay, it looks good there. And then we're going to multiply that by alpha r to the negative 1. We got a half. Okay, sweet. And then we have alpha e squared plus 12 alpha e cosine omega t plus 36. I just want to make sure I got that e right there. I'm sure I did. Yep, we did. And we got that e right there. Alright, this is brutal. Alright, so bracketed in, and this is a 1 inverse square root. So we have to the negative 0.5. Okay, booyah. And then we have 12. I'm going to bracket in the numbers. Alpha e. Negative 1. Sine. And see how I bracket in the negatives like this? It's the only way I can keep track of them. Because this is not a minus. You know what I mean? It's just a multiplication that you're multiplying it by. You know, we have a negative sign, theta, beta. Alright, negative 1 sine omega t, and then omega. Holy hell, we did it. Alright, so this should give us 2.22. Do you think it will? Hell no. Ah, bummer. Oh, whoa. We should be in radians. Yep, we are. Oh, so it didn't like this it didn't like the square root. Yeah, something got really funky. I'm gonna. Oh man, I'm bummed about this. But I guess we could go through and check our errors just to see if there was anything going on. Sometimes if you start out with a negative, it's got to be a negative. It can't be a minus. You know what I mean? You can't have a minus. So now we're good there. So we have negative 1 divided by 1 plus all this jazz squared. Yeah, so we have e plus 6 plus e cosine omega t. That got squared. Multiplied by e to the negative 1 sine omega t to the negative 1. Alright, and all that's squared. Okay, so yeah, we're good there, but this bracket got out of control. No. So this bracket was wrong. Sorry about that. So this bracket is right there. And then once we square this, I need a bracket. So this is the funnest part about finding errors, because we need to do this negative 1 divide. That's why I don't do divided by. Why not just throw all this up top? You still got to bracket it in, though. We still have to have a bracket between the 1 and then the 1 plus all that squared and then end bracket. Okay, so hell yeah. So if that, I think that was my error, and now we might be good. Nope. So, it was brutal. So, but hopefully we can kind of figure out what's going on, because we should be good. I mean, we're taking the inverse cotangent. I mean, I think we're good there. Yeah, and we flip this. So, yep. That looks a little funky, but whatever. E to the negative 1 sine omega t to the negative 1, and then we square it. Now we're going to multiply by e to the negative 1 sine omega t, omega e to the negative 1 sine omega t to the negative 1. Look good there. plus 6 plus e cosine omega t e to the negative 1. Negative 1 sine omega t to the negative 2 cosine omega t omega. Alright, end bracket. Alright, plus negative 1 divided by the square root of 1 minus r to the negative 2 alpha e squared plus 12e cosine omega t plus 30. Yeah, I think I'm done with this because everything looks actually fairly decent. I'm not finding any errors. So it might be something actually more funky than I can deal with at this point. But that's exactly why, yeah, I can't deal. So anyway, let's go to the error. I don't know, do we just, is it just getting rid of that? Is that all it wanted? Oh, I'm sure not. Alright, so we have to be done with this, but that's what you would do. This one was just super big, and I don't know, I'm kind of bummed that it's not even giving me an answer. But such is life. That's why you have the derivative calculator. That's why when you get derivatives, there's just, I mean, if you get more than, yeah, if you get more than 2 terms for your derivative, you know, or 3 terms, I mean, this is hellacious. So there's just no point. Yep, just use the software to bust out the derivative. But it's kind of a cool way to see if you can make errors and then find them. All right, we can do this a little bit more because we definitely need to bracket that in. So, and we haven't done that yet. So we need to bracket all this in because we're multiplying it by that. So I did find one thing. So hell yeah, and yeah, add it all the way across. Whew, that's a big one. Yep, we need a bracket there. Okay, hell yeah. And then I just need to make sure that bracket's the same size. Yep, so we did. We bracketed that in. And I'm just going to double check all the way across. Okay, so, and then we're going to start in on this. Booyah, divided the square root. Now we come up to here. Alright, to the negative 0.5. Okay, hell yeah. Ah, damn it. Alright, so still think I'm done. Alright, yeah, I'm striking out on this one. Such is life. But, you know what I mean? I think we did it. I'm pretty satisfied with this video. So, hell yeah.